Today in the workshop, we'll be working with some inexpensive RF modules. I'll show you how you can use these to transmit data between two Arduinos. You'll learn a bit about how amplitude shift keying works, and we'll build a remote temperature and humidity sensor. So stay tuned and welcome to the workshop. Hello and welcome to the workshop. Today we're going to be adding radio communications capabilities to our Arduino projects using some very inexpensive RF modules. Now there are a number of ways of adding radio communications capabilities to your projects. Wi-Fi is an obvious choice, and that would allow you to integrate your project with your existing Wi-Fi network and with all the devices that are already on it. Bluetooth is another method of communicating between your project and things like your phone or your tablet or a nearby computer. There's also the nRF24L01 modules. These are very popular for adding two-way radio communications between two Arduinos, and you can separate these by a fair distance with the correct antenna. But we're not covering any of those today. We will in future videos. But today we're going to focus on some very inexpensive RF modules, a receiver and a transmitter that work on the 433 MHz band that you can buy for about $2 for the pair. So for less than the price of a cup of coffee, you can add radio communications capabilities to your Arduino projects. So we're going to look at how these modules work, some of the antenna considerations, and how we can use these to make our Arduinos talk to each other wirelessly. Now, before we start working with radio devices, we need to discuss a little bit about the regulations involved in doing that. Every country in the world has a regulatory body that is responsible for controlling how communications are used within the country. In the United States, the Federal Communications Commission, or FCC, takes care of this. The Canadian Radio and Television Commission, or CRTC, is responsible for this in Canada. And in the United Kingdom, Ofcom, or the Office of Communications, are who regulate radio usage within the country. Now, your country, if I haven't mentioned it, does have a regulatory commission. I've got a link in the article to a good Wikipedia list that lists all of them for all of the countries in the world. Now, the transmitters we are going to be using work on the 433 MHz band. This is a UHF band, and this is sometimes referred to as LPD 433. Now, globally, these transmitters are generally allowed to be used as long as they are low power and intermittent. In some European countries, you can actually run them at a bit higher power and at a more constant signal. But if you wanted to do that within the United States, for example, you would actually need a valid amateur radio license. Now, the experiments we're about to do make use of them in a very low power mode, and the range is restricted to a few meters. Now, in no circumstances should you attempt to amplify the output to get a higher range. You can work with the antennas, but the range is limited and it is what it is. Do not try to make a more powerful device which could cause interference with some of your neighbor's equipment and which can also get you in trouble with the authorities. So having said that, let's proceed and move on with our radio experiments. Now here are our two modules. This module over here is the transmit module, and this one is the receive module. Now, there are very few connections on these modules, which is what makes them so easy to use. On the transmit module, this outer pin over here is the data connection, and amusingly, they've got the word data written backwards on these modules, so that's AT-UD, but it's really data. The middle pin is the VCC connection for the positive voltage, and on the transmitter module you can use any voltage from 3 to 12 volts, and the higher the voltage you use, the more powerful the module will be. And the third pin is the ground pin. There's also a connection up at the top over here for an antenna, and we'll talk about that in a moment. Now, on the receive module, it's also very simple to connect. Although there are 4 pins, there are really only 3 connections. The outer pin here is the VCC, and unlike the transmitter module, this needs to be 5 volts. The pin on this end, on the other end, is the ground pin, and the center two pins are actually internally tied together, and this is the data out pins. There's also an antenna connection on this as well. It's down over here by this little coil. Now you probably noticed that both the receiver and transmitter have a place where you can solder an antenna, and you're going to need to do this because without an antenna these two devices are limited to ranges within a couple of centimeters. It's not very practical. With an antenna you can extend it a lot further. Now the antenna isn't anything fancy. It's just a piece of solid 22 or 24 gauge wire, but the length of it can be important. When you're building an antenna for a radio device, you need to look at the frequency that you're using and look at the wavelength of that frequency. Now 433 megahertz falls in the UHF or ultra high frequency band, and the wavelength of a 433 megahertz signal is 69.24 centimeters. Now it's customary to cut an antenna to a half or a quarter wavelength. A quarter wavelength is often used, and a quarter wavelength of this signal would be 17.31 centimeters. So that's the length you're going to want to cut your wire to for your antenna. Now you can reduce the length of the antenna if you wish by coiling it. You can just use something like a pencil or a pen and coil the wire around that to make the antenna shorter and yet still as effective as it would be if it was a long antenna. So you're going to want to do that to both of your modules. The RF modules we will be working with use a technique called amplitude shift keying, or ASK. Like all forms of data transmission, this is a method of modulating a carrier wave. In our case, the carrier wave is a 433 megahertz signal. This is very similar to the analog technique of amplitude modulation, which you might be familiar with if you're familiar with AM radio. It's sometimes called binary amplitude shift keying because there are only two levels we are concerned with. You can think of it as an on-off switch for the carrier, in which a digital 1 turns the carrier on and a digital 0 turns it off. Without modulation, this is what our carrier wave would look like. With amplitude shift keying, the digital 1 turns the carrier on, whereas a digital 0 will turn it off. The advantages of ASK is that it is very simple to implement. It is quite simple to design the decoder circuitry for an ASK system. Amplitude shift keying also needs less bandwidth than FSK, or frequency shift keying, which is another common modulation technique. The disadvantage, however, is that amplitude shift keying can be corrupted by electrical noise and interference. In order to experiment with these RF modules and our Arduino, we are actually going to need to use two Arduinos, one for the transmitter and one for the receiver. And I've got a setup like that right on my workbench right now, with this being the transmitter and this being the receiver. And in my first demonstration, all I am doing is I'm sending a canned message from the transmitter over to the receiver. You'll notice I'm running my transmitter on batteries. The receiver is still connected up to my computer because I want to use the serial monitor to display the canned message. And if you wish, of course, you could use two computers if you happen to have that, one for the transmitter, one for the receiver. Otherwise, you'll just have to load the code into them one at a time and then run the transmitter on a battery or on a power supply. Now, for our first demonstration, we're going to make use of a library called Radiohead, not to be confused with the musical group. This is a library that has a number of functions that allow you to transmit and receive data on all kinds of radio links, including these 433 megahertz modules. This takes care of a lot of the problems you would have if you tried to transmit and receive manually meaning without a library. The reason is that noise that you'll encounter on the receiver can be quite severe, and so a number of keying techniques such as asynchronous shift keying and all have been employed in order to combat that noise. If you try to do this manually, you can do it with code, and there are a number of examples up on the web and on YouTube of folks who show you how to do this. A lot of them use an analog input port for the receiver and look at a threshold, and if the level is above a certain level, they consider it to be a digital 1. If it's below a certain level, they consider it to be a 0. But by using a library like the Radiohead library, we can eliminate all of that and just focus on actually building something that is reliable and that works. However, if you do feel like experimenting with doing this manually, I'd encourage you to take a look at articles and at videos that show you exactly how to do this. So let's take a look at how I've hooked up everything for our first demo, and then we'll look at the sketch that I'm using for it. Now here's the hookup for our transmitter. It's actually very simple. Obviously you're going to need an Arduino Uno, and you are going to need a transmitter module, and those are the only two components you'll require. Now the VCC, which is the center pin from the transmitter, is hooked up to the 5-volt output of the Arduino. The ground from the transmitter, of course, is hooked up to one of the Arduino ground connections. And the data input to the transmitter is hooked up to pin 12 of the Arduino. You will need to use pin 12 because the library actually expects to be transmitting data on pin 12. Now let's take a look at the receiver. Now the receiver hookup is just about as simple. Again, you'll need an Arduino Uno. You will need one of the receiver modules. Now VCC, which is the pin on the far left, is again hooked up to the 5-volt output of the Arduino, and the ground is hooked up to the Arduino ground. Now you can use either of the two center pins as an output, as they're actually tied together anyway, and this is connected to pin 11. Again, our Radiohead library expects the receiver input on pin 11. And now that this is all hooked up, let's take a look at the sketch that we'll be using to send data between the transmitter and the receiver. Before we work with our sketch, you're going to need to obtain a copy of the Radiohead library. Unlike other libraries that we've used in previous videos, this library is not available by searching in your library manager. You'll actually have to go and download a copy from the website. I have a link in the article associated with this video so that you can get this library. Here's the Radiohead page, and you'll find the library right at the top over here. The current version as of this recording is 1.83, and it's available in a zip file. So download that zip file into a location that you're going to remember, and then head into your Arduino IDE. So here I am in my Arduino IDE looking at the transmitter sketch. Before I use it, I'm going to have to install the library I just downloaded. So if you go into Sketch and go into Include Library, you will see Add Zip Library. Select that and navigate to the directory that you downloaded your library. And look for the library and then click OK to install it. I won't do that now because I've already installed the library into my IDE. Once you've done that, you can proceed with the sketch. Now the Radiohead library actually includes a number of smaller libraries, and the one we are going to be using is one called Amplitude Shift Keying. So we are going to include the Radiohead Amplitude Shift Keying library, and we will also need to include the SPI, the Serial Peripheral Interface library, that is included with your IDE. The reason for the SPI library is that we're actually sending and receiving serial data, so the Radiohead Amplitude Shift Keying library makes use of some of the functions in that library, so include the SPI library as well. Next, we're going to create an object, which I call RF driver. After that, in the setup, we are going to initialize that object. And then we go into the loop. We're going to create a character, and we're going to call it message. This is one long character of multiple characters, and my message is welcome to the workshop. Now it is important to note that of course you can use any message you wish, but you'll need to know how many characters are in the message, and that includes the spaces and the exclamation mark in my message. In my case there are 24 characters. If you choose to change the message for your demo, just count the number of characters, because you're going to need that when we do the receive sketch. Then we're going to send that message actually. Now this is the format that we're sending it in, and we need to know how many characters we're sending. And the Arduino string length command will give us the string length of a string. So the string length of message in this particular case is 24. And then we're going to wait until the packet has been sent. Sometimes this can take a bit of time. And then we're going to delay for a second and go back up and do the whole thing again. So our transmitter is going to continually broadcast our message, "Welcome to the workshop." And so now that we've seen the transmitter sketch, let's take a look at the receiver sketch. Now I've connected my computer up to the receive Arduino. The transmit Arduino is currently being powered by a 9-volt battery, so it should be transmitting our message right now. Of course, you could use another power supply for that Arduino, or a second computer if you have one. Now the receive sketch starts off identically to the transmit one. We'll include the radio head amplitude shift keying library, and we'll also include the dependent SPI library. And again, we're going to create an object, which we've once again called RF driver. Now in the setup, we'll initialize that object, and we'll also set up our serial monitor, because this is how we're going to display our received message. In the loop, we will set our buffer to the size of the expected message. So as you recall when I talked about the transmitter, you need to know the number of characters you're sending. I'm sending 24, so I'm going to initialize my buffer with a size of 24 characters. And I'll also define buffer length as the size of that buffer. Now we're going to check to see if we've received the packet and if it's of the correct size. So we do that with this statement here. And if we have, we'll display that on the serial monitor. I'm going to display message received, and then add a space, and then I'm going to actually print the entire buffer. And then I'll go through the loop and do it over and over again. So now we'll upload that to our Arduino and see if we're going to get any messages received. So we'll go and open our serial monitor. And it's not uncommon to start off with a little bit of the buffer like we did, but as you can see, we are receiving a message. And welcome to the workshop. Now just one final word on the demo that we've just done before we move on to the next one. It may seem like this is just a simple demonstration and it doesn't have very many practical uses, just sending the same message over and over again. But one thing you can actually use this demonstration for is to check your antenna arrangement with the two devices, with the receiver and the transmitter. Now on my devices, I've used a piece of wire as my antenna, as about 17.3 centimeters long, because, as I said earlier, that's a quarter wavelength of the 433 megahertz signal. And because my transmitter is being powered by a battery, I can move it around the room. I can move it into another room. I can see how far I can actually transmit by using this demo. And I can also experiment with doing things like coiling my wire. I can maybe make it a different length or something. Maybe add another 17 centimeter wire onto the ground. That is another common way of creating an antenna with two wires, one on the ground and one on the antenna side. So you can do some experimenting to find out the maximum range and also find possible sources of interference in your home. For one thing, I'm a source of interference. I notice that the closer I get into my experiment, the more I seem to drop off packets. You'll notice in the last demo that the welcome to the workshop wasn't coming up every time, and I think a lot of that was because I was near it. I noticed as soon as I backed away, it came in more consistently. So again, that demonstration, while it seems simple, can actually have a practical use. So now that we've seen that, let's move on to bigger and better things. So for the final demonstration today, I'm going to show you how you can send data from a sensor over the RF modules from one Arduino to another Arduino. Now for my sensor, I've chosen a DHT22 temperature and humidity sensor, which I've got on my breadboard with the transmitter right now. Now I chose the DHT22 for a reason. First of all, it is a practical thing to try to measure temperature and humidity remotely. But secondly, we are sending two pieces of data, the temperature data and the humidity data. So this sketch will illustrate how we can send two pieces of data over the wireless link, and you can extend upon this concept to send as many pieces of data as you would like to. So let's take a quick look at the sketch for the transmitter that I've used. Now the only changes we're going to need to make to the wiring are to the transmitter. Our receiver will be identical to the last experiment. So on the transmitter we are going to add a DHT22 temperature and humidity sensor. We're going to connect the VCC from the DHT22 to the 5 volts on the Arduino. We'll connect the ground on the DHT22 to the Arduino's ground. We're going to send the output from the DHT22 into pin 7 of the Arduino's digital I/O ports. And that's it for the wiring. As I said, no changes to the receiver are required. So now let's take a look at the sketches we'll use in order to send the data from the temperature sensor to the remote Arduino. So here's the sketch that we're going to be using for our transmitter. Now this sketch is going to require two additional libraries that you might have in your IDE if you've done some of the experiments in my previous videos. We need the Adafruit AM2315 library and the Adafruit Unified Sensor library. Now we used these libraries before in the video that we did with the HCSR04 ultrasonic sensor. We used the DHT22 in that video to measure temperature and humidity and factor it into the speed of sound. So if you followed along those videos, you probably already have these libraries. If you don't, I've got details in the article accompanying this video on installing them using the library manager. You could also take a look at the older video to see how to do that. Once you have the libraries, we can begin with the sketch. The sketch starts as our previous sketches did by including the Radiohead ASK library and the dependent SPI library. Next, we include the DHT library. We define a couple of constants. These are both for the DHT22. DHT pin is the pin on the Arduino that we've connected our sensor to, and I've defined it as 7 because I'm on pin 7. If you wish to use a different pin, just change this number. We also need to define the type of sensor because our library is capable of driving several temperature humidity sensors. DHT type is defined as DHT22. Now a couple of variables. These are both floats and they represent the humidity and the temperature. The temperature will be in degrees Celsius, by the way. Next, we'll define a couple of output strings. We need strings to format our outputs and not floats. So strHumid will represent the string value of the humidity, strTemp for the temperature, and stRout is our final formatted output. As with the previous videos, we'll create an object which I'm calling RF driver. And now we need to initialize a DHT sensor, and we do that with this command. Now in our setup, we need to initialize the ASK object as we did before, and we also need to start our sensor, and we use a DHT begin command to do that. And now we're into our loop. We'll start the loop off with a 2-second delay. This is required so the DHT22 can stabilize itself between readings. Next, we'll assign those floats we defined earlier to both the temperature and humidity values we read from the sensor. Now we're going to convert these to strings. So strHumid is going to be the string value of the humidity, and strTemp will be the string value of the temperature. We're now going to combine the two strings, and we're going to put a comma in between the two of them. This actually creates a comma delimited string that starts off with our humidity value and then with our temperature value. Now we're going to create a character as we did before. We'll define the character message. The star in front of this means it has multiple characters within it. And we are going to use stRout, which is the string we just formatted, and this formats the string as a character. Then it is the same as our previous transmit sketch. We'll send out the data that we just formatted, and we will wait until the packet has been sent, and then we'll go back to the top of the loop and do it over and over again. So about every 2 seconds we will be sending out a string that has the temperature and the humidity value with a comma in between the two of them. So now that we've seen the transmit sketch, let's take a look at the receive sketch. Now our receiver sketch starts off very similar to the last receiver sketch we looked at. In fact, you can use the last sketch to look at the raw data that we're sending out of the transmitter. You'll see the comma delimited string. You'll also see some junk right after the string, and that's a null character that's sent after every line. It won't be displayed in this sketch. So we start the sketch off as we had before with the radio head amplitude shift keying library and the dependent SPI library. We're going to define output strings similar to what we did in our transmit sketch. So we have a string for the humidity, the temperature, and for the final output. We'll create an amplitude shift keying object, and we'll initialize this object within the setup. We're also going to set up the serial monitor because this is how we're going to display our temperature and humidity data. And then into the loop. Now the loop starts off the same as the last receive sketch. The only difference is we set our buffer size to 11 because that's the total length of our comma delimited string. Each one of the temperature and humidity variables need 5 characters. That's 4 digits plus the decimal point. And there's also the comma that we have in between the two of them, so the total is 11 over here. Once again, we'll check to see if we've received the packet and if it's the correct buffer size, and if it is, we'll go down into this part of the code. Now, we'll take our string out, which is a string, and we'll take it as the characters that are inside our buffer. Now, these are characters, so we need to convert them using a string command. After that, we are going to use this for loop to split them into 2 values using the comma that is part of our comma delimited string. Unlike other programming languages, the Arduino does not have a command like a split command that can just simply do this. So this for loop over here will accomplish splitting it into 2 values, which we define as the humidity and the temperature. Now that we've got those 2 values, we simply send them out to the serial monitor. So I've already loaded this up to my Arduino, so let's take a look at our serial monitor and see what we're picking up. And there we go. It's a pleasant 23 degrees Celsius and 47.4% humidity inside the workshop right now. So that's about it for today. As you see, these little RF modules may be inexpensive, but they're actually quite useful when you want to send data in one direction. Now obviously these are not as advanced as Wi-Fi or Bluetooth solutions or even solutions based around the NRF24L01, but for many applications it's all you'll need, and for $2 you really can't go wrong. Now the last demonstration we did showed how you use the DHT22 sensor and sent both temperature and humidity data by combining them onto a comma delimited string. And you can extend this technique for other sensors. You can send more than 2 pieces of data at a time, and you could also use the analog inputs on your Arduino. So let's say you wanted to get the input from a joystick. You could use the X and Y axis on the joystick to drive 2 of the analog inputs and send that data over the Arduino to a remote. So this could make a very simple remote controlled joystick arrangement if you wish. There's a lot of possibilities over here. Anyway, I hope you enjoyed this video, and I hope it opened your eyes to some of the things you can do with these very inexpensive RF sensors. Now, I'd really like you to subscribe to the channel if you haven't done so. I would really appreciate that, and that way you'll also get a notification every time I put a new video out. And I'm going to attempt to put more and more videos out because I know people have been asking for that, and believe me, I am trying. So, once again, I thank you very much for joining me today, and I hope to see you again soon in the workshop. Take care of yourself, and goodbye for now.